All right. Happy Tuesday, everybody. Good afternoon. Glad everybody could make it. Happy we're all here. So I know it's been a couple weeks. I might just kind of arrange some stuff on the screen here. Uh, yeah, so we were out a week for spring break, and then I was out last week with some normal, boring life stuff. So it's been a couple weeks since we met. I guess so. A couple announcements. Midterm grades are all up, and homework grades are all up. I'm going back through all the project two stuff to check on the bonus question. For everyone who did the bonus question, I haven't had time to look at that uh, to the extent I would like to. So I'm going to go back over that. So some grades might change based off the bonus, but only in the upward direction. So don't worry about it. Otherwise, and let's see. Yeah, so that's it. Grading stuff. We're starting a new unit today, so we're looking at Unit 4, which is actually extracting and classifying features. So I'll talk a little bit kind of about, the lead up to this once I start the lecture proper. But that's what we're doing. So we're in Unit 4, which is there are two units left, this one, and then, another one that's a little bit more application focused. So for this week and the next few days, we're just going to be talking about how we actually sort of extract a feature once we find it. Kind of we've got everything in the feature space, and we have a pretty good idea of what the feature vectors are and the source and the target. So now the idea is how do we extract the features we actually want, and once we have pulled them out, how do we classify them? So that's going to kind of be where we start our discussion today. And then Thursday, I will put out the next assignment, which will cover this unit 4. And we'll kind of go from there. So what I'm going to do here real quick is make sure all these screens are kind of cleaned up so you're not staring at any stuff that's mine. Looks like. All right, we're good. So let me go ahead and start the screen share. All right, so we've got that. We've got the chat and the Discord open. For anyone that kind of has questions you want to drop in the chat. So, like I said, today and for the next few lectures, we're going to be talking about feature detection, right? And then in particular, feature extraction and then feature matching. So we talked a little bit about the idea of feature matching before the break and sort of establishing what that kind of means, what is feature matching, kind of what is a feature. So what we sort of established before is this idea that feature matching is where you are identifying key points, right? With, we talked about SIFT and SURF and this idea that, key points are sort of scale invariant. And so we can look inside the wavelets for SURF or inside the scale space for SIFT. And those will give us back key points and information about them. So kind of their parameters. And we can then go in and we can take, a feature or an object usually that we want to detect in our target image. So we'll sort of have our source image that is just the thing we want to find in our target image. And what we'll do is calculate a feature vector for that source, in this case, that object, with the idea being we can match key point feature vectors to that, which is what we do. So when we run our algorithm, so far SIFT surf, or orb is the one we could actually use in class because surf is behind a licensing paywall. But the idea is, sift or surf or orb is going to go into your image and it's just going to find every key point, right? We're not really looking for the feature we want initially. We just want every sort of feature that stands out as a key point. And then we want to take those key points and compare them all against the feature vector of our target, our object. And the ones that match close enough, we say, okay, that's what we're looking for. We're going to extract that feature and call it, a soccer ball in this instance. So thus far, what we've been really looking at is this idea of, kind of feature matching, where you're comparing, a feature vector from a source to the feature vector for all the key points. And, as we've gone through kind of the first half, I guess probably more like 2/3 at this point of the semester, what we've talked about is the low-level feature detection, which is looking at things like edge detectors and things you can measure in a color space. Typically, like low-level features, you're usually going to get just from pulling information directly from the sorry, I lost my train of thought because I'm sharing the wrong screen. Sorry for everyone staring at Discord. Right. All right, can everyone see the slides now? Okay.
Yeah, Professor, we can see the slides.
All right, dope. Yeah, so like I was saying, we've got our source, which in this case was our soccer ball. We've got our source feature vector that we're going to find, and then we're going to try to match that feature vector with the feature vector of every key point in the scene. So when we look at these, I'm going to come back here, these low-level feature detection, that is when we're looking at edge detectors, because every point on an edge is different from every point not on an edge, so you can kind of conceptualize edge pixels as a feature in their descriptor matrix. In that case, it's just 0, not edge, 1 edge. And so when we think about low-level feature detectors, we're usually working directly with the pixel values. And that was kind of what defined this idea of a low-level feature as well. It's a feature we can get to and access and understand without having to do anything to the pixels themselves. We can just move between color spaces and apply some algorithms and find what we want. For our mid-level features, which is what we discussed through the end of the last unit, was this idea of a parameter space. And in particular, we talked about the hue transform a lot. And this idea was we're now not looking directly at the information inside the pixel. We are looking at information derived from the information inside the pixel. So once you get to that mid-level feature detection task, you have abstracted the image past the point of being a normal boring image a human looks at, right? You have added a layer of abstraction to this where you're no longer working with the image directly itself. You are working with information that has been extracted from the image. And so that's the idea of this parameter space, and again with the hue transform, where you are looking at something about the image instead of just the image. High-level features, where we're talking about detection and classification, that is where we work in the feature space, right? So we've gone not only from, a low-level task where we're working with the pixels, and we sort of move past that mid-level space where we're looking at parameters that are still, make a lot of sense to a person. I can look at a hue space and a hue transform and understand the R theta of it all, for high-level feature detection, especially when you start talking about machine learning models, the information inside a feature vector is by and large nonsensical to a human. It's sort of like trying to see inside the hidden layers of a neural network. Each activated neuron will typically contain what looks to a person like trash, just a bunch of really weird random parameters it has come up with that get the answer it wants, right? And that's kind of the issue with machine learning models and high level feature detection and classification is, even without a machine learning model, even if you're just kind of doing it sort of the archaic way that I learned before, machine learning really took off, you're still, a feature space is just a bunch of numbers that, doesn't really make sense to a person. At that point, it is all just stuff that a computer can understand in a way that it can do good math at to get answers. And so that's kind of our ladder up through feature detection. And now here we are, we're sitting atop kind of the pinnacle of detection where we're looking at these high level features. And so now the goal becomes, if I've got, my SIFT, my SURF, my OR, my hue transform, anything that is looking for an edge or a key point, I'm essentially asking it to find all of them, right? I add some thresholding, I can add some bounding boxes, some masking. I can tinker with convolutional kernels if, I really want to get my hands dirty. But at the end of the day, those are going to essentially give me, within those parameters, everything, right? The next step that we have to solve, sort of the next big problem is, I have extracted every feature and I have the feature vectors for those in the feature space, and I have the feature vector for my thing in the feature space. So how do I go from having every feature to the feature I want, right? We can detect all these features, but the idea is now, how do we extract the features we want? So this just goes along with what I was, just kind of talking about with this idea of, we work in color spaces for, our low level stuff, and we work in parameter spaces for our mid level stuff, and now we're working in the feature space. And again, we can think of the feature space as a coordinate system where instead of an XYZ point or an R theta point, we have a point in a very, very high dimensional uh, coordinate space, usually, hundreds of values. So we've still got this idea of, vectors in space, and we're in our feature space, and each vector is some point within that space. And so the way we get the features we now want out of this is we have to find a way of comparing feature vectors to determine if they're essentially close enough to each other in feature space. So, if you think about it sort of physically or geometrically, you want to know which feature vectors in this multidimensional space are, sort of physically, geometrically, how you want to think of it, near each other, right? So if you think of 3D points, you group all the points around, your feature, and everything that is within some distance in the feature space, you're going to extract, and everything outside that distance of the feature space, you're going to throw out. And we talked a little bit about what types of features can be in a feature space. And kind of like I mentioned, SIFT and SURF do this a little bit, where they pull out a lot of random numbers if you go tinker with it. But essentially, the feature space can be whatever works. Usually, it's going to kind of, you can think of it as a space that stores information about things like color and edges and shapes and textures and distributions. And so, really, anything you can kind of think of as a property of an object in an image, you can think of as something that will exist in the feature space. last thing we talked about for spring break and midterm and everything is now we're going to go into talk in detail about actual feature matching techniques. And so the three we discussed is this idea of Euclidean distance or brute force matching, where you just compare parameter by parameter between two vectors in a feature space, which is very, very slow, right? We kind of talked about how it's a really good way to do it in much the same way brute force is a really good way to do anything, so long as you don't care about processing time. And you can imagine, a Euclidean-based feature matching technique, when you're talking about feature vector with 500 or so parameters, and you think, even on good computers now, brute force is going to really bog down whatever you're trying to do. And if you're doing like an object detection classification application in the real world, don't want the bottleneck being finding features in the first place. You don't want to spend all of your time just doing this brute force to extract the features you want before you even get to any kind of the fun, meaningful sort of CV stuff you can do with these algorithms. So we're going to be talking about feature matching techniques. So you can see here, I'll probably kind of demo all of these as we go, just especially to show how much longer like a brute force runs in something like Flan. Also, it's not on here, I should add it, but we'll talk about YOLO, which is the you only look once feature extractor, which is fast, but as the name implies, when you're only looking through the image once, it can not always be the best. But I'm going to add that on because I do want to talk about it. I actually used that in some studies I did a while back when I still had a grown-up engineering job, and it was a pretty interesting algorithm. All right. So we've got our feature matching techniques, right? We've kind of listed some of them out here and, kind of italicized the ones we're going to spend more time on that actually, matter and you can actually use. I think, by this point in your college career, you're probably familiar with brute force versions of everything. So other than to see how woefully inefficient it is, we probably won't talk much else about it. Before we get to the idea of feature matching and feature extraction, we're going to talk a little bit about anomaly detection and sort of what is anomaly detection, what is the theory behind it. So an anomaly is essentially anything that does not match all of the things around it, right? It's, something that clearly does not belong where it is or is very different from everything around it. And in computer vision, when we talk about an anomaly, it's essentially something in the image that deviates to a statistically significant amount from what you would expect to find in the image, what the expected norm is. And so when we talk about it, with our soccer ball example, the idea is, the normal, right, what we would expect when we look at the field is it should all be field, right? And we can define that statistical normal quite readily, with things like it's all this color and it's all this intensity, right? Or it has all of the same texture. And so in that case, the ball would then be the anomaly, and we were trying to find that anomaly within the field. So all of the feature detection algorithms we've talked about and all of the stuff we're going to talk about going forward, they're a bit like an anomaly detector with extra steps, right? They're all sort of birthed into this horrid world as anomaly detectors, and then are made much better and made specific for computer vision. So before we delve all the way into the computer vision stuff, it's worth talking a little bit about the idea of anomaly detection in general and how that has spun out into these detection and classification algorithms. So when we think about it from this perspective, essentially all of the key points it gives us, these algorithms of SURF, all of the key points are basically anomalies. They are points in the image that are statistically different enough from the rest of the image that it is flagged as, in our language with SIFT and SURF, a feature. What those features are kind of fundamentally is just an anomaly, right? All of the key points I'm going to find are going to be the things that are significantly statistically different from everything else in the image. And that's where things can get a little tricky when we think about feature extraction, is it is kind of on a per image basis, the way it is done just generically, right? If we don't do any pre-processing, then it's looking for key points that are different from the image, right? And if we have a big noisy image like we saw through our demos where we have the tiger statue and we run our SIFT and our SURF, we get back 50, 100 key points, lots and lots and lots of key points, because the image itself is varied and there's a bunch of stuff in it and it's relatively noisy just from a foreground background everything in their perspective. And so first, that makes it hard to set a normal, right? Versus if we're looking at just a field with a ball in it, it's very clear what defines sort of the normal field and very clear what defines an anomalous soccer ball. Whereas when we have these other noisier images or bigger images with more things in it, what's normal for the whole image is not going to be particularly normal for several sub-regions inside the image. And so that's how we end up with so many key points, is there's not enough uniformity in the background of the image to determine a statistical norm that is good enough to only pick out certain points that I really, really want. And so to kind of overcome that issue within these images, we need to kind of think a little bit more about what anomaly detection means and kind of how we do it, and how these anomalies we find are key points in an image. And so that's what I mean when we get back our list of key points. We're essentially getting back a list of everything that looks different from everything else in the image after it's averaged out. So one of our jobs in computer vision as smart computer vision people is to kind of understand the concept where all of the features are being picked out in relation to whatever else is in the image. And so how can we do a better job finding only the features we want before we have to then go in and do all of our feature matching, right? Can we be clever in how we look for these features by being clever in what we know about them? So to kind of expand on this topic, there's this idea that within computer vision, we can sort of say there are three main types of anomalies. So sort of three things we want to find when we're doing computer vision. So there's this idea of a structural anomaly, which is essentially either a structure in an image or a form of a structure that really shouldn't be there. So this would be, if we were looking at our soccer field with a soccer ball on it and put a plane in the middle of the soccer field, right? That would be a structural anomaly because the plane shouldn't be there and it looks nothing like anything around it. You can very easily pick it out based on more of a geometry kind of feature vector, where you think if I'm trying to match features for this soccer ball, and the soccer ball I find is bushed flat, right? That will kind of pop out as a structural anomaly where, okay, right, I found this soccer ball, but it's deformed. Um, and so you see structural anomaly detection uh, most often in sort of industry, so like industrial tasks. There's lots and lots and lots and lots and lots of people working on CV for defect detection on assembly lines. So like, can I put a bunch of cameras on my conveyor belt and can I use them to find sort of faulty parts or defects as things are being manufactured? And conversely, once you have a system that's been built, some sort of physical thing, you can use computer vision to then kind of observe it and make sure there are no defects in the final product. But in general, that's where you're going to see structural anomalies. They'll also pop up on like GIS and remote sensing applications where you're expecting some sort of surface and you find stuff you're not really looking for, and that's kind of where structural anomalies come into play. We aren't going to do very much with structural anomalies because we're going to focus a lot more on contextual anomalies because that is the most sort of common CV task that we use for anomaly detection. That's this idea that this object is perfectly normal, like a ball is it's a sphere, it's fine, it's just a normal thing that exists in the world, but we shouldn't find it flying through the air or something similar. I mean, I guess if you kicked it on. A little better examples. This idea of a car on the sidewalk, right? So the idea is you're looking for something that is, a normal thing, but it is not supposed to be where it is. And so a lot of anomaly detection and a lot of computer vision is based around this idea of context. And, what things should be where they are and what things should not be where they are. However, when we think about it, we don't necessarily need to think about this as something that is unusual as to where it is, and I know that sounds a little confusing, but for us in CV, this idea of context isn't necessarily sort of a semantic thing for humans to think about, like a road or sidewalk. A context would be a grass field. So a grass field is kind of our normal, that's our context. And so if there's a soccer ball on the field, it doesn't look like the field, it's not part of the field, it has all these different properties. So kind of within the context of the image itself, it is anomalous. So basically, it's kind of just a fancy way of saying, I want to set the context, which is what is normal in my image. And by normal, I mean sort of the statistical baseline, right? And then I want to find things that deviate from that. And that is what we will focus on, not entirely exclusively, but mostly we're going to be talking about this idea of an anomaly within the context of the image. And then the last one you can think of as this idea of a behavioral anomaly, which is just when something inside of the image, or for behavioral anomalies, you're going to be using video footage, so video. you're looking for something that is behaving irregularly. And in this case, when you think about behavioral anomalies, you're typically going to be sort of in that machine learning realm where you have trained a model to understand, what normal behavior is. You've trained all of your feature detection and extraction on what to look for. In this case, it would be a person. So you've already kind of built all the things that understand the features that make up a person, how to extract the features associated with a person to get that feature sort of detected and you know where the person is. And then you would have, your model trained on, if I've detected a person feature moving through this video, what is the typical behavior for, a person walking through this area. So that's something we'll talk about it kind of at the very end when we do some 3D applications. But in general, while we're talking about feature extraction and classification, we're going to be talking about it in a contextual context, a contextual way, I guess. So to start sort of at the very kind of bottom of the ladder of finding contextual anomalies, the most kind of basic way, the easiest way, the most straightforward way is to use a histogram. And so when you create this histogram, you're basically, and I know everyone knows this, but you're taking some measurement from the image and you're putting it into bins and seeing how many pixels or parameters or features fall into that bin, right? You're just sort of counting everything that's in the image, binning it all according to some, what's the word I'm looking for? Some parameters, like it could be color, so you bin all the red, all the blue, and the green into this histogram, and you count the number of data points in each bin and turn that essentially into a normal distribution or a normal range. And so this is what I mean by the sort of broader context of the image, right? When we're looking at this contextual anomaly, right? If we create a histogram of everything in the image, then we've binned it all and we found our normal range or normal distribution. That essentially is kind of the normal context of the image. Everything in the image we would reasonably expect to fall within one of these bins, within sort of the distribution of bins. So we've created this histogram or normal distribution that determines, this is sort of the expected context. This is what the image should kind of look like if there were no anomalies. Okay. And then what you do is you look at bins with very few sort of members, so bins with very low frequencies. And what you can do is, if something is not occurring very often, if something is only showing up a few times when you build your histogram of the image, it kind of follows that it only happens a few times, and it is not happening sort of in the same way all the other stuff is. So we just have all these low frequency bins kind of lying outside of our histogram, and then we just sort of slap a threshold on it. So, if the number of times this thing shows up in the image is way lower than everything else, then I'm going to say all of the things in that bin are anomalies, and I'm going to go and I'm going to look for them. There are kind of a couple problems with this approach. One is that, and we're going to talk about it next class because I didn't have time to get all the code ready. I wanted to get ready for today. But one problem is that this kind of anomaly detection has a huge false alarm rate because it's just very sort of, I don't know, it puts everything into these broad categories and then flags everything that falls outside sort of that own distribution. And so you can have something occurring a few times in an image that, you know, show up a few times and we don't really care about them and they're not really anomalies, but because it's only, you know, there to a limited extent inside the bigger image, it's still going to get flagged. And so this is only really good for looking directly at information inside pixels because you can't really build a normal distribution of features from features in a parameter space and definitely not from a feature space. Right. And so what that means is it kind of ultimately boils down to this idea that, you know, a histogram isn't really a parameter space or a feature space, and it's not really a feature vector. It's just a statistical measure of the image as a whole. So when we're thinking about doing anomaly detection in images and histograms, which we're going to see in a minute, we're never really going to do because it is really not a good way of doing it. But it essentially is you kind of think of it as like the feature vector for the entire image. And then you're just looking for any features that fall outside of the expected distribution, sort of. So, like I said, it's only good for applications using information inside a pixel. And even then, it still has an extremely high false alarm rate. And it takes a lot of sort of hands-on tweaking of um, thresholds. Like the thresholding in this kind of anomaly detection can, you know, be great or it can be terrible, and it's never really consistently one or the other. So again, you know, I'm giving you all the reasons you should never use this thing. I'm teaching you how to use, but for some things it is still kind of useful, and it can be pretty useful for especially stuff in the IR space, where if you're looking at kind of a heat map, it's very easy to say there should be, you know, some sort of distribution of heat over a certain area. And so if one spot is a lot hotter or a lot colder, you can get at that just using histograms and thresholding. So it's okay for intensity. It's okay-ish for color. There's some things you can do with it with texture. As far as an actual useful tool, like I said, we're not really going to use it. It's just important to sort of establish this is the concept of anomaly detection within a computer vision feature extraction task uh, within within the context where the normal distribution is the context, and anything that sort of falls outside of that normal distribution is an anomaly. But it kind of helps show how the image as a whole, in and of itself, is kind of the context, and you want to find the normal of the image and then find things that aren't within that normal range. But like I said, with noisy images, images with a lot of color, images with a lot of stuff in them, you can't really make a good histogram of a normal distribution because there's just too much stuff in the image. And it just sort of washes everything out into, you know, I don't really know what a normal is, so I'm just going to flag stuff at random as the algorithm runs. So one space this is a good anomaly detector in, and like I said, I'll cover some more next time once I get a chance to write some more code, is IR and hyperspectral images. And like I said, you know, in an IR image, everything should be one temperature, right? In general. So if any one thing shows up a lot, I can do a histogram of temperatures across the image and find outliers in that. There's some spots that are much hotter, colder, kind of like I said. This is actually quite useful in medical image processing because if you think about an MRI or an X-ray, there is a normal version of that, right? There's the way it is supposed to look. You know, if your bone isn't broken or your ligaments aren't torn, you haven't, you know, anything like that, or you don't have sort of black spots to signify, you know, some sort of cancerous growth, right? We have a very, very well established normal for what a healthy human should look like. Um, and so we can easily, you know, kind of use this histogram method where if something inside this image that I know what should look like doesn't, you know, match, stands out, doesn't kind of fit in the bins I've established before, then I can flag that as an anomaly. And so, you know, with medical applications, this hasn't taken off until machine learning has really taken off. And while I do gripe about AI/ML quite a lot, just in general, this is one place that it's very, very good because you can take a model, and like I said, we have tremendous amounts of data on normal for medical images. And so we can use those with machine learning to train the model on essentially how to cut out lots and lots of false alarms while picking out smaller anomalies. And so it's twofold in that, you know, we can trust the results because they're good and we've trained and we've done all of this stuff. And because it's been trained and knows so much of what to look for, it can find smaller anomalies that a person would find or a person would flag as anomalies. So this isn't a great way for things like object detection, object classification, or image segmentation, because, like I said, in color image is not really clear what you can look at, versus a grayscale image or an intensity image, like if you were doing HSI for some hyperspectral data, then it does work because you know what normal is, and so we can find things outside of normal. So I have a small notebook here, and I was going to run some of this stuff on. So this is just run out by hand how to find a histogram. So we've got an image, got a red, blue, green, and so we have 256 bins, kind of one for each value a pixel can take, right? Pixels 1 to 255 of the red, blue, and green. So we just have bins for each of those pixel values for each of those color values for each pixel, right? So you can see we've got our RGB bins. And every pixel that falls within those values gets dumped into that bin. And then to detect anomalies, we've set this threshold, and that's something we can tinker with to, you know, get more or less anomalies detected. And once we find those, we can kind of flag them as anomalies. And so if we run this code with this one, so if we run this code with our RIT Tiger, we get this output. So let me zoom this a lot, right? And so we can see it's not great for this color image because there's a lot of kind of background noise because it is going to average everything out. It's that background, it's all zeros. And so it's going to flag these anomalies that look, you know, different. And you can see we got some of the R, the T, the I, and then just a bunch of mess where the tiger is. And you can see because we've got, you know, a lot in the red channel in particular, or RGB that makes up the orange, that essentially it's finding anomalies everywhere that isn't orange, because all the bins are based off of the color of the tiger plus a little bit of black plus a bunch of white. So anything that isn't orange, it's going to say is an anomaly, right? And so we get this back, and there's not much we can do with it at this point, right? Like, this was just a really roundabout way to get the same kind of crappy output I would get from running a really dumb edge detector on a really poorly filtered version of this image. When we take this and now look at the thermal image, so if we want to just look at, say, a handprint, right, now what we see is, a little bit more again. Yeah, so in this case, it has found that handprint. So this is an IR image of just a handprint on some glass. And we want to go in and find anomalies. And here in this case, it was able to find it. It was able to find it quite easily, because the context of the image, sort of all of the image together, is this gray field with some black stripes through it a little bit. And so when we average all of that stuff, everything sort of averages out to a nice normal gray. So I am able to get a distribution of what's normal within the entire image. And then I can find the things outside of that normal, which in this case stand out very strongly, which is that handprint. And so this is, kind of the basics of anomaly detection with computer vision or in an image, right? We're going to do much better ways of this, like with Canon, Flan, and YOLO, but the idea is still the same. The idea is still that we're doing a context-based anomaly detection where we decide what is, normal for the image, what is, not a key point, not an outlier, not an anomaly, just whatever we expect to be there. What on average is just normal the image. And then to extract our features, we want to find things that are outside the bounds of what is normal for the image, and then figure out what those are, and then use that information to do something. And so with histograms, you can just kind of see that at a very low level, where it's just outside this distribution. As we go on, like with Flaming YOLO, the idea is, it's a feature vector that is outside of all of the normal within the image, that is inside the normal of my source feature vector. So that's just the real basics of it. I'm going to stop sharing now and kind of wrap it up here for today, so I can get some more notebooks ready for Tuesday. Yeah, I guess, are there any questions, comments, concerns? Everything kind of making sense so far? Just Professor Durst making you learn more random theory.
Excuse me, Professor.
Yeah.
Yeah, I had two questions. Of first of all, about the histogram method that we talked about earlier for at least in terms of anomaly detection. So that in that way, like you mentioned, there's like a certain threshold, like through which, like if it doesn't meet, is that for all of the intervals through that we create, or does only one not have to be met in order for it to be classified as an anomaly?
It depends on how you set it up. The one I'm doing here, kind of the most simple one, is that if it is outside of sort of anything, right, then it's an anomaly. You can basically do, like, I don't want to say sub-histograms, but separate. So you could do one for just red, just blue, and just green, and then only flag stuff that's outside the normal for the green color. But in general, it is just sort of one lump. This is normal, and if it's not normal, it's an anomaly. And other than making different histograms, you can't really do a lot of clever stuff with it.
See, I see. Okay, yeah, no, I was just a bit confused by that since it just because I kind of thought about each feature. But yeah, also another question. This kind of related to the midterms. So I know you mentioned for the homework too that the extra credit for that would still be good, still needs to be graded. Is that the same for the midterm as well, or
Just
is that
the
added?
That's been added to the midterm grades. So I'm just going over it now for the homework.
I see. Okay, yeah. Thank you, Professor.
Yeah, of course. All right, cool. Well, if there's nothing else, I'm going to go ahead and pause the recording and end the lecture here.